Check it out now, y'all.
nanoHUB-U Online Instruction.
Welcome back. This is lecture 3 of the 5th week. Today we're going to talk about different battery architectures. To this day, all our designs have focused on a battery that has a porous anode, a separator, and a porous cathode. Okay? I mean, conceptually, we've been thinking of this particle size distribution that ideally may be spherical or away from spherical. And this is a very popular design. In fact, most of the batteries that people use these days have this architecture. Okay? And one of its main advantages, is dirt cheap to make. Okay? And with that economy associated with that, which is really driving how these systems are being made, we have been able to move forward in this field by basically trying to find the best possible particle size, the best thickness, both in electrodes and separators, and basically move the field forward. Now, what people have been trying to do recently is trying to get rid of all these non-idealities that this type of architecture has. The first one is, well, this battery has these random events that are hard to control. I mean, even if you have perfectly monodispersed particles, you can see that you will develop clusters. You will develop regions where lithium will still try to go around it, but it will take some time. As you know, particles are not necessarily spherical, and that will add additional losses to the system. We'll focus some of those irreversible reactions that we've been talking about. And well, in general, the biggest loss, as you saw from the previous lecture, comes from taking a lithium ion, crossing that separator layer, percolating between the particles, inducing with that additional losses, and then reacting with an electron, which, by the way, had to cross the entirety of the anode, go through the load, come back here through to the back contact, percolate between the particles through this network of conductive material, and then react at the surface of the particles. So you can see the thickness of the electrode, the ones that we're using to store as much charge as possible, is working against us. Okay? So, but basically the biggest drawback is that we will always have to traverse the entire cell, and this will get worse the thicker the electrode is. And well, another big issue is that we always have to go somewhere between 30 to 60% porosity in order to be able to open those paths for lithium to go through, for the reactant to go through, and maximize the power that we have in the system. And in the previous lecture, we were talking about how would we optimize that porosity and that thickness to basically include both the thermodynamics and the kinetics, at least the polarization, the ohmic polarization losses in our system, assuming a certain type of reaction as it's occurring. Okay, so in that sense, if you believe what happened on the previous lecture, we're throwing away at least half of the energy that we could actually use, and that is bad for performance. Okay, ideally, because the way we pick this architecture, we have all these losses that pile up as the reaction proceeds. Therefore, we need to make really big cells. Basically, our cells are pretty bulky in order to be able to get the charge out of it. We would like to make them smaller. We would like to make them denser. But the denser a cell is, the more losses across these layers is. And so we have a problem. So people have been trying to basically start deviating or improving this design to try to make a better cell. One of the first things that people tried, this is in the mid-90s, what they try to do is basically try to control the porosity of the system. Basically, for example, you can think of electrodes where basically you have these gradients of porosity. And if you think about it, conceptually it makes sense, right? If on one end of the cell I have this very open path through which lithium can go through, then that will give you, at least on these particles over here, much faster access for lithium. Maybe your reaction zone will move further in, but you will be able to get more instantaneous power, and the back could be utilized to basically supply a core of energy for the cell. Or maybe there's some advantage of clustering of the particles, giving an average porosity. Why? Because, well, maybe if I put these particles together, maybe my diffusion distance will increase, but I will make these paths to the back bigger. Or maybe what you want is to control the porosity, the particle size itself, which if you think about it, we really haven't introduced that much into our description. But people play these games, and basically you can play games of changing the porosity and making that porosity a function of the reaction of the thickness of the electrode, or basically of position, making that reaction zone that we talked about to be very much dependent on the porosity profile. And if you do that, well, some of them have advantages with respect to the other ones. For example, it's not the same to have a gradient whose slope is negative than have a gradient whose slope is positive, or it's not the same to have a gradient that is linear with respect to one that is quadratic. Some of them will be much harder to make than others. Obviously, in colloidal techniques, you can use them to improve on them, but really the biggest issue when trying to make these cells really boils down to trying to find a processing technique that gives you an edge with respect to what's currently on the market without compromising the cost that you will add to it by processing it further, by not just simply mixing the powders and the electrolyte, but by finding some sort of organization. Okay, so this is a very straightforward thing. You can think of it as the very first step, but we're still limited by what porosity we get. And in fact, you can see here how for these designs, in some cases, we start with a 40% porosity, which is relatively high, and as we go back in the thickness of the cell, it just gets, the porosity drops to 10%, really showing you that on this end, you will have more energy more power than in the back where you have more energy. Or you can start instead of trying to implement this structure, basically trying to implement one where the gradient is linear, opening those paths, right? So the processing technique will always be critical of specifying how a cell behaves. So, but you can see we're still limited by this window of basically 25 to 40% porosity, which is where people typically are. So, and by doing that, we have in the lowest limit, we have already thrown away at least 25% of our material simply because we want to be able to access more. So some recent designs are, for example, the ultra high energy density systems where basically you go below that 20%, you try to go to the 10-15%, or basically shave it down so that the amount of energy density, as you compare with the classic designs, as you can see here, you basically increase it by orders of magnitude by densely packing those cells, right? And you can see here in the micrograph how the particles are so tightly packed that lithium really has to make an effort to go through. And as this cell is assembled, and you can see it's basically a solid green body that is very thick, that basically what you do is you have a container through which you put your structure is basically assembled in this container. You can actually get a very, very nice responses, but you can see the size of the structure as compared to in this case to a penny, right? In order to get some energy out of that. So really, you will always be able to use this. You could use it for high energy density applications, but you will still be limited on power. Power really becomes the biggest issue here because you really have closed the paths for diffusion in your system. So the same people that developed this, what they did is they just added additional paths for transport. You can see here the same density on the matrix of particles, what really gives you an additional amount of energy, but you basically space so a set of linear pores through which you infiltrate electrolyte that you can use to optimize what would be the best possible design to basically increase the power density. How is that process? Well, basically they do use some co-extrusion, and in this case what they do is they have the particles and they just put some fibers of carbon and they assemble them and extrude them, and then just do this several times. They just iterate between mixing the fibers with the powders and keep extruding them and after burning it out, okay, they get these linear pores through which they infiltrate the electrolyte and use that as locations where you can have a high transport path to basically access the back of the electrode. Okay, you can see this idea really goes beyond what's typically done and allows you to basically increase the energy density of your cell, while at the same time try to keep your power density in check so you can actually use it for higher applications. Now, this is the simplest idea, okay, and it's really not fair for me to say simplest idea, because really it is a very engineered, advanced way to design a battery, okay, but it really is still thinking of a cell where you have an anode layer, a separator, and a cathode, and people have been also trying to get away of that, and actually in this case in the early 2000s, what people do is just try to blur the boundaries between of what an anode, a separator, and a cathode is. And here what you have is that the cathode material is really basically interpenetrated with the anode material. And people what have been using here is just basically these lithographic techniques that people have used in the past for MEMS and structures like that. You can basically decrease the ohmic loss by bringing much closer both electrodes, and by making the electrodes themselves smaller, you basically can bring, by a factor of 2 or 3, sometimes even by a factor of 10, bring together the electrodes and increase the density, the amount of energy that you have together. And well, these are just some structures that I found online of what has been patented. You can see in some of them you have the electrode where you have this almost like cone-like structure. Basically, you can think of these platelets that have these high diffusion paths, and the counter electrode, or in this case something that basically almost like a jigsaw puzzle, basically locks very nicely with the counter electrode, and somehow you have to fill in these gaps with respect to the other electrode. Or this one over here, for example, where you can see you have this like almost gear-like structure that you basically match the counter electrode and use that to basically minimize the transport from one electrode to the other. In this case, the mixture of electrolyte and carbon black is removed, and the only thing you have here is basically electrolyte or separator material where only the lithium ions can flow, not the electrons, right? And when that happens, basically you force the electrons to go effectively through the active material, removing with that the losses occurring between the two layers. But by changing the path through which electrons go through, you basically force add another layer of losses. In this case, you make the electrode material to be the region through which the losses will be held, right? For one of these structures, let's just say for this one, because these platelets are so large, basically lithium flows freely through these, and basically they react inward. So you can think of that structure as the material is coming through, right? And they don't have to be necessarily solid. You can think of these mixtures of electrolyte and particles now forming these structures. So what we have learned about the ohmic losses, about the reactions on mold, you can directly apply that. So now we have these losses across these different layers, and now we have one running from one end of the platelet to the other end of the platelet, as we take this platelet to be basically one of these units, okay? And that changes the contribution. Now we have not only the losses through across the separator, if we have one, okay, but now we have to account for the loss as a result of us going through the system, and the electrons are being transported by the back of the structure. So this structure, this design, if we apply Newman's reaction zone model, will only be advantageous if the thickness of the separator is greater than this weighted thickness of the length of these posts, right? If the post is too long, that increases the losses. Why? Because again, electrons now have to travel the length of the rod. But in any other case, you can really actually increase your density by doing that. People have searched this type of design for several years now, since the early 2000s. So, but these are just platelets, right? Even though we really have brought much closer the electrodes. So other structures that people have proposed are, for example, defining like rods of structure. Basically, you have cathode and anode. You can see here how these black posts corresponds to the anode material and the green post corresponds to the cathode. And in between, you just have a layer of electrolyte that you're using to extract material. And you can apply the same idea where, again, basically you go from your electrons are traveling the length of one post, react with the lithium that travels between the anode and the cathode, having these really small distances now to traverse, really decreasing the losses, sometimes by a factor of 10 just from doing that. Okay, in other cases, what people have done is basically have your anode layers, your anode rods to basically be surrounded by cathode material, and in between you put the electrolyte, so that, and by completely removing this anode separator cathode architecture, you really bring them much more closer. But you can see that just from doing that, it will become very easy for, if a rod is not well aligned, to induce an internal short circuit in the system. So this is well, the top plans of that structure. And this is just some early attempts on creating those architectures. And well, if you don't do this right, you can make these rods basically start touching each other, or you can make them fail at the bottom. And after some time, if you're not careful at making them, you can end up. You have to control very carefully how you deposit these, because you can end up with poorly assembled structures. And then in this case, for these structures, you can see that the lithium is coming from the side. So in this case, as compared to having one platelet, you have more area in this case in every direction through which lithium will come through. So we can think of that also in the context of our reaction zone. And in this case, our reaction zone is moving radially to the center of the structure. And if you do that, and if you go through the steps of accounting how much current, how much charge is going through, and how much it has, what is the shell size that as it has intercalated in this highly dense but porous structure, you can come up with a reaction zone model that now goes as the square root of time, right? And if you do that and put it back into your reaction zone model, you really have the opportunity to get voltage profiles that differ in shape with respect to the classic design, because now we have much more area and that we're using in order for this material to proceed, right? And now, when will this system will be useful? Well, only when this contribution, the radius and the thickness of the size of the post is controlled enough. So in this case, there's a specific rule that you have to derive to make this design work. Basically, if this term is not small enough, you will get a voltage that is lower than you would get from a classic design. And this means, if you go through the math of this, you will realize that you really need very skinny columns in order for this design to work. Okay, but if you do, then you could get performances that are comparable or larger than the classic designs. With that, of course, putting any thought right now to the economics of how this would work. Some ideas on how this was implemented was, for example, this design that was published by Koyama and co-workers. And in this case, here you have the posts, and you can see in the center, these are in this case are graphite posts, and they put a ring of lithium. So in this case, lithium comes through the sides to intercalate on the post, and the post basically just expand and contract. It was really not used, this specific design was not used as a battery, but because of the large expansion and contraction that the posts have, they've really been using them as a means to actuate, to basically move something using this type of battery. It's a very nice implementation though, and it really shows you the potential from going away from the classic design. This post, you can see, are pretty big. We're talking about 400 micrometers by 700 micrometers at the base, and well, you can use a lithium cobalt oxide type structure or a graphite structure, and you can get very nice responses. Now, That's on that end, on where you really control very carefully the structure of each of the electrodes. But another thought, another school of thought as to how a battery should be assembled corresponds to self-organizing batteries. And many thoughts have been brought up as to how to assemble them. Some of them really correspond to just put the particles in, say, in a beaker and let these particles basically start assembling chains or assembling structures that allows you to do that. Some people recently have sought approaches such as using viruses as nucleation sites. Others have really relied on methods like colloidal theory to assemble them. And others, for example, really what they have sought is try to use structures that they can easily process in the lab. In this case, this is a foam structure where basically you use a carbon foam as your anode and then just start plating with, say, first electrolyte and then the cathode material in order to basically effectively use it. If you do that, then you have this large porous structure with very large openings through which material can flow in and out. And if you do this, you really can get very nice responses, okay, and this just corresponds to another pattern as I found it, and well, and you can see the advantage of this. The main advantage of this specific design is that the anode itself is one entire structure that is very well connected, and the holes themselves associated to this foamy-like structure, when you fill them with the counter electrode, if you do it right, you basically can have another structure that is very well connected. So you really have this bicontinuous or tricontinuous structure if you put it in between a layer of electrolyte. So it really, people have come up with these really neat ideas on how to make cells. Another idea was on self-organizing batteries, where you have the particles of one material basically try to stick to each other and form chains, while in the positive electrode, the platelets also will start attracting each other, but cathode and anode materials basically will repel each other, leaving with that a natural distance that will lead to a higher response. If this kind of device works, then you could get a very nice response, and it really doesn't boil down to actually spending a lot of money in making the structure, but then just allowing for the thermodynamic and kinetic conditions for the cell to form. Something very recently that was done, basically the creation of, in this case, colloidal structures that are used in this case as a template to basically etch out the material and basically use that template as a conductive framework, or to put particles in there. People have used them basically to basically have the particles right next to each other, suggesting with that you can actually get a lot of response. And actually, if you compare those to what you get, what other technologies develop, you can see how those structures can give you a higher power density, because as you stack them and organize them, you basically decrease the distances for the ions to go through, and the conductive network that you set up really gives you a very nice place for those electrons to be exchanged. And well, here they really try to make the case as to how your energy density can drop up to an order of magnitude just from doing that, and well, give you in this case better reliable performance. One final description that I want to talk about corresponds to the flow batteries, and in this case what you do is you put your powders in the electrolyte suspension, and basically you just pump it through one region, so that in one side you have the cathode material that is in this case expecting to be lithiated, the anode material that is fully lithiated, and then you bring it to a region where basically through a porous separator in between, they exchange electrons, they exchange lithium ions, and you get the charge out of that, and then the properties of both electrode materials basically change, and you move them and store them in a different place. And that gives you an opportunity to keep the reaction zone within one distance, to basically keep the reaction contained in a very small place, and to completely be replenishing the active material and always be delivering peak performance. These designs are very new. Many of them have already gone into production. Some of them are really mechanically so big that they cannot be used for transport applications, but more to basically large storage applications, basically to store energy, for example, like solar or eolic. You can see how you could put these giant tanks of fluid flow energy to store charge and put them there. So at the end of the day, you can get the charge out. And the performance in this case seems to be very nice, because as you change the rate of how the material behaves, you can really store different amount of charge and always be working very close to peak performance. And that, I think, it's a very nice concept. And well, that's the end of the lecture. Thank you very much.